This course module covers the technical fundamentals of the basics for gas analysis. In this course, we would like to explain about some of the important parameters of the gas analysis. At the end of this course, we will understand what our analyzers indicate, how to convert different units, how to calculate and indicate the emission. Please imagine the following scenario. It's a CEM system. CEM means continuous emission monitoring. The CEM system monitors pressure, temperature, flow, dust, moisture, and the different pollution components, and transfers data to a data acquisition system. The customer has to report the emission to the authorities. The problem is that they must report the emitted gas concentration in milligrams per cubic meter under normal conditions. But our analyzers do not measure under normal conditions. What do the analyzers actually measure? We have two groups of measured components. 1. Requested components. 2. Utility components. The requested components are specified in the legislation. For example, dust, NO, nitrogen monoxide, NO2, nitrogen dioxide, SO2, sulfur dioxide, CO, carbon monoxide, HCl, hydrogen chloride, NH3, ammonia, etc. The utility components, pressure, temperature, flow rate, oxygen O2, water vapor H2O, are needed in order to be able to convert into normal values. What are norm values or norm conditions? 1 standard cubic meter Vn is the quantity of gas that under a pressure Pn of 1013.25 hectopascal, at a humidity of 0% dry gas, and at a temperature Tn of 273 Kelvin, equal to Tn equals 0 degrees C, occupies a volume V of 1 cubic meter. In addition to these normal conditions, the emission is calculated to a certain reference oxygen level to be able to compare emission values. The reference oxygen value depends on the individual emission system, and it is mentioned in accordance with the authority. Typical reference values are 5, 6, or 8 volume percent O2. Summary. For the emission, all measured gas concentration values are calculated according to normal conditions. Measurement components are typically indicated in volume concentration ppb, ppm, volume percent, or mass concentration milligrams per cubic meter, grams per cubic meter, kilograms per cubic meter. 1. Volume concentration. Volume percent means 1 part per 100. ppm means 1 part per million. ppb means 1 part per billion. 1 volume percent equals 10,000 ppm. 1 volume percent O2, oxygen, in N2, nitrogen, means from 100 parts there is 1 part O2 and 99 parts N2. 1 ppm O2 means from 1 million parts there is 1 part O2. It's just a ratio between different parts. Can you imagine having 1 million little balls? All balls are black, just 5 of these are blue. You have to find these 5 blue balls. Then you find 5 ppm. 2. Gas density is expressed in kilograms per cubic meter, grams per cubic meter, or milligrams per cubic meter, and means mass per volume. 1 kilogram per cubic meter equals 1,000 grams per cubic meter, equals 1 million milligrams per cubic meter. The gas density depends on pressure and temperature. The gas density is higher when the pressure is higher and or the temperature is lower. gas density is proportional to P divided by T. We have to understand the difference between volume parts and gas density. An illustrated explanation of gas density. The gas density becomes lower if the balloon rises and falls as a result of the external air pressure. The balloon expands and its volume increases, but the number of molecules in the balloon remains constant. The concentration in volume percent does not change, regardless of the height the balloon reaches. That's to say, the 21:79 ratio remains constant even if the balloon expands, because the external air pressure drops. The gas density, mass over volume, changes with the external air pressure. The volume increases as the air pressure decreases, and the number of molecules in this volume remains constant. That's to say, the mass over volume becomes smaller. The relationships are similar if the volume changes due to temperature alterations. ppm and volume percent indicates the ratio or the concentration. When the volume of a gas composition changes, for example because the pressure or temperature differs, the ratio between the parts in the total volume does not change. Grams per cubic meter and milligrams per cubic meter indicates mass divided by volume. This is called gas density. Pressure and temperature differences influence the gas density. In order to be able to compare or to convert between those values, the values for pressure and temperature must be mentioned. The calculation between volume concentration, ppm, and mass concentration, milligrams per cubic meter, is done by using mole mass and mole volume. The mole volume under normal conditions, 273 Kelvin, 1013 hectopascal, is 22.41 liters per mole for all gases. The mole volume at 25 degrees C, 298 Kelvin, 1013 hectopascal, is 24.46 liters per mole. C, milligrams per cubic meter, equals C, ppm, multiplied by mole mass divided by mole volume. Example: 21 volume percent O2 equals however many grams per cubic meter under normal conditions. Mole mass for O2 is 32. C, milligrams per cubic meter, equals 210,000 multiplied by 32 divided by 24.46 equals 300,000 milligrams per cubic meter equals 300 grams per cubic meter at 273 Kelvin, 1013 hectopascal. Now you can easily calculate 21 volume percent O2 into grams per cubic meter at 25 degrees C, 1013 hectopascal. C, milligrams per cubic meter, equals 210,000 multiplied by 32 divided by 24.46 equals 275 grams per cubic meter at 298 Kelvin, 1013 hectopascal. 21 volume percent O2 is 300 grams per cubic meter at 0 degrees C, 1013 hectopascal, but only 275 grams per cubic meter at 25 degrees C, 103 hectopascal. As next, we would like to know how a different pressure changes the result. In day-to-day operations, we usually resort to tabular data. This table refers to the conversion rates between 0 degrees C and 1013 hectopascal. This information must be visible in all tables used. We just calculated the conversion from 21 volume percent O2 into grams per cubic meter under normal conditions. 21 volume percent O2 is 300 grams per cubic meter at 0 degrees C, 1013 hectopascal. Now we would like to know the conversion for 21 volume percent O2 into grams per cubic meter for an altitude of 4,000 meters, which means 600 hectopascal. We know from all gases P multiplied by V divided by T is proportional to mass. P is pressure, V is volume, T is temperature, M is mass. When V and T are constant, then P is proportional to M. And now we can calculate 21 volume percent O2 at 1013 hectopascal corresponding to 300 grams per cubic meter. 21 volume percent O2 at 600 hectopascal is corresponding to 178 grams per cubic meter. We realize for the same volume concentration, here 21 volume percent O2, we get a different mass concentration per volume when the pressure changes. Our next parameter is the dew point. The dew point is used to say something about the moisture content in a sample gas. Instead of the dew point, we could also mention the water content in volume percent or in grams per cubic meter. The dew point is a very common parameter for gas analysis. But what is the dew point? We all know that our ambient air can absorb humidity. The amount of humidity that can be absorbed is dependent on the temperature and pressure of the air. We know that warm air can absorb much more moisture than cold air. The dew point is a water-to-air saturation temperature. The dew point is associated with relative humidity. A high relative humidity indicates that the dew point is closer to the current air temperature. When the dew point remains constant, that's to say the absolute water content remains constant, and the temperature decreases, relative humidity increases. Relative humidity of 100% indicates that the dew point is equal to the current temperature, and that the air is maximally saturated with water. If the temperature decreases to lower than the dew point, we will get condensation. Or a typical example in which condensation occurs, for example when glasses fog up when entering a warm room from the cold. At the cold glasses, the warm, wet air cools down and the water condensates. Another example. The temperature is 20 degrees C and the relative humidity is 100%. That means the dew point equals 20 degrees C. Then the absolute water content equals 2.3 volume percent. Look at the following table. When now solely the temperature increases to 30 degrees C, the dew point remains at 20 degrees C. The water content is still 2.3% volume H2O, but relative humidity is only 55% now, because air at 30 degrees C can absorb 4.2% volume H2O to be saturated. In this table, we find the water concentration in volume percent and in grams per cubic meter at 0 degrees C, 1013 hectopascal for the different dew points. Now let's summarize this learning module. So, what have you learned so far? Typical terms associated with the gas analyzer system. Typical units of volume gas concentration, volume percent or ppm. Typical units for mass concentration, gas density, grams per cubic meter, milligrams per cubic meter. Conversion between these units. The terms dew point, relative humidity, and moisture content, parameters for the emission calculation under normal conditions.